विद्यार्थी मित्र, आपण ऍसिड्स आणि बेसेस या टॉपिक संबंधी काही माहिती घेणार आहोत. ऍसिड्स आणि बेसेस ही सोल्युशन्स आहेत. दीज आर द सोल्युशन्स ऑफ आयदर सॉलिड्स और लिक्विड्स और गॅसेस इन सम सॉल्व्हंट. जनरली दिस सॉल्व्हंट इज वॉटर. आपण याचा अभ्यास कशासाठी करणार आहोत की त्यांची स्ट्रेंथ म्हणजे वेदर दे आर स्ट्रॉंग और वीक. दुसरी गोष्ट त्यांचं पाण्यामध्ये जे संहती किंवा कॉन्सन्ट्रेशन या दृष्टीने मोलॅरिटी आणि नॉर्मॅलिटी आणि ह्या दोन्हीचा उपयोग न्यूट्रलायझेशन किंवा टायट्रेशन रिएक्शन्स मध्ये या दृष्टीने आपण त्याचा अभ्यास करणार आहोत. मग असे म्हटल्याप्रमाणे acids and bases are the solutions obtained from solids, liquids or gases in water. उदाहरणार्थ HCl, that is HCl gas dissolved in water, or sodium hydroxide, that is NaOH solid which is dissolved in water, which is generally called as alkali solution. Acids and bases are known from long time. Generally it was known that acids they generally form blue litmus red while alkalis form red litmus blue. One more thing is known that acids generally dissolve many of the metals. While studying acids, one famous scientist Arrhenius put his theory for which he received Nobel Prize. He says that acid gives H plus ions while bases or alkali give OH minus ions when dissolved in water. When acid or base is dissolved in water, it dissociates or ionizes, and the amount of ionization being dependent on the strength of the reagent. A strong acid or base is completely dissociated while a weak acid or base is partially dissociated. The chemical compound which gets dissociated into ions in dissolved state is called electrolyte. So acids and bases are considered as electrolytes. याची आपण काही उदाहरणं बघूया. स्ट्रॉंग ऍसिड्स आणि बेसेस यामध्ये HCl म्हणजे परक्लोरिक ऍसिड, H2SO4, HNO3 आणि अल्कली म्हणजे NaOH आहे. आणि वीक इलेक्ट्रोलाइट्स मध्ये ऍसिटिक ऍसिड, अमोनिया, फिनॉल, फॉर्मिक ऍसिड, ऍनिलीन असे काही पदार्थ आहेत. Thus, the strength of any acid or base can be described quantitatively using the term strong and weak. There is one more concept to describe acids and bases. For acids, basicity is the concept, that is the number of replaceable hydrogens present in the acid. For example, HCl is giving one proton, so it is monobasic. H2SO4 diabasic, H3PO4 that is phosphoric acid is tribasic. For bases or alkalis, acidity concept is there, that is the number of replaceable hydroxyl groups in a base. For example, NaOH that is considered monoacidic, calcium hydroxide is diacidic, while aluminum hydroxide is triacidic base. Whenever we are considering acids and bases, if we are considering their action in aqueous medium, they react to form salt and water, which is generally considered as neutralization reaction. For acids and bases, some other theories were also put up there. Bronsted and Lowry in 1923 put one theory. They actually work separately, but their theory is called as Bronsted-Lowry theory. It assumes that a transfer of proton generally takes place from acid to a base, so they form a conjugate pair. So acid after losing the base proton will form the base, while base after accepting that proton forms the conjugate acid. So conjugate acid-base pair, that is the concept there, and so this theory is applicable to non-aqueous solvents also. As I described, these reactions they are shown which can be indicated by half reactions And then for the complete neutralization reaction, the combination of half reactions that can be considered. One more theory is given by Lewis in 1923, which is still advanced one. As per that theory, an acid is a substance that can accept an electron pair or donate proton, while a base is a substance that can donate an electron pair. So that is Lewis concept, which is useful for redox titrations as well as for formation of coordination compounds. We have talked about the strength of the acids and bases. Now let us know something about the concentration of their solutions. How much quantity of solute, that is any acid or base, is present in solution, to express that is the concept concentration. For expressing concentration, the important concept, that is molecular mass of solute, that is used there. Molecular mass or molecular weight is the relative mass of molecule with respect to C12, that is carbon atomic weight, which is assigned value 12. So molecular mass is generally expressed as gram mole. So this quantity is gram mole. Molecular mass is actually the sum of all the atomic masses of that particular molecule of that chemical substance. So for any chemical substance, a gram mole is defined as the molar mass of that substance expressed in grams. Actually, the concept is very useful here because one mole, that is containing one Avogadro number of molecules. So whenever we are considering these reactions of acids or bases or any different types of chemicals, we are considering the number of molecules which are reacting together. So gram mole concept, that is very useful. Whenever we are trying to find the concentration of acids and bases with reference to H plus ions for acids or OH minus ions for bases, the number of H plus or OH minus ions produced in aqueous medium can vary from substance to substance. For example, we have talked about basicity of acids or acidity of bases. So a new concept other than atomic mass or molecular mass is considered, which is considered as equivalent weight, which is especially useful for neutralization reactions and related technique, titrimetry. Equivalent weight is that weight of substance which combines with or displaces 1 part by weight of hydrogen or 8 parts by weight of oxygen or 35.5 parts by weight of chlorine. Generally, gram equivalent, it is the concept used, which is equivalent weight expressed in grams. We can have some smaller units. For example, 1 millimole is 1000 part of 1 mole, while 1 milliequivalent is 1000 part of 1 equivalent. Using this, for the solutions, we can express the concentrations. For example, if 1 liter of solution contains 1 gram mole, that is having 1 molarity. Similarly, there is one more concept, that is normality, where 1 gram equivalent present in 1 liter of solution is having concentration 1 normal, or if we are using smaller units, 1 milliequivalent in 1 ml solution, if it is there, it is called as 1 normal solution. So we have talked about these units. When we use them for acids and bases, we are using somewhat simple concepts there. Equivalent weight of any acid is the weight of an acid which contains 1 part by weight of replaceable hydrogen or proton. For base, it is equivalent weight is the weight of base which contains 1 part by weight of replaceable hydroxyl group. So using these concepts, we can talk something about the normalities of acids and bases And if you want to calculate them, we can use this formula. Normality for any acid is equal to basicity into molarity, while for the base, normality of it is acidity into molarity. Whenever we are expressing the actual amount, then it may be the weight dissolved per liter. So using either normality or equivalent weight, we can express that particular unit. When we are knowing the normalities and volumes for one particular reagent, we can calculate that normality of other reagent. For example, if we know for the acid, we can calculate for the base. Or if we want to dilute some reagent, if we know the strength of concentrated solution, we can find out the strength of dilute solution using this type of equation, which is N1V1 equal to N2V2, which is known as normality equation. Using this relationship in neutralization reaction, one can find out the concentrations also by titration, about which we will be knowing a bit later. For the concentrations, we can consider one example here of sulfuric acid. Generally, concentrated sulfuric acid, which is obtained by dissolving sulfur trioxide gas in water under pressure, we get the molarity as 18 molar. As it is diabasic acid, its normality is 36 normal. If we get from this dilute solution, for example, 3 molar, then it will be having normality 6 normal. How to prepare that? Let us see. If you want to prepare 1 liter of 3 molar H2SO4, normality equation can be used as it is indicated here. Dilute H2SO4 and concentrated H2SO4, for which this equation that is indicated. Dilute will have the molarity 3, its volume will be 1000. Concentrated sulfuric acid is having the normality 36. So we want to calculate the volume of that. So using this equation we can calculate, and this is the volume 83.33 ml. Now how to prepare this? Generally we take in a beaker which is kept in water bath, water, and to that we are adding drop-wise concentrated acid with stirring that solution. You may be knowing that these reactions are exothermic, that is, heat is generated. So always you will have to take care that you should add to the water the reagent, that is either acid or in case of bases the alkali. So this precaution should always be taken. Related to concentrations, let us solve one more problem. The problem is, calculate the number of moles of the solute in 1 liter of aqueous solution of sodium hydroxide 10% solution. Whenever we are expressing the concentration, percent, that is another concept for expressing it. 10% solution of NaOH means 10 gram of solid sodium hydroxide dissolved and diluted to 100 ml. So NaOH we are taking in grams, while the volume of final solution is in ml. So percent weight by volume, this is the relationship. Now how to calculate? Now we want to prepare 1 liter of 10% NaOH, so it will require 100 grams. Now we will require the molecular weight or molecular mass of NaOH, for which we can use the atomic weights of hydrogen, oxygen and sodium to calculate the molar mass of NaOH. If we add them, we get that molecular mass as 40 grams. So 1 gram mole of NaOH will be 40 grams. So if we dissolve and dilute that to 1000 ml, we get one normal solution. Now we want to dissolve 100 grams to prepare these 1000 ml. So it will be 2.5 gram moles in that solution. So the molarity of that solution will be 2.5 moles. So this is something about the concentration. Now, using such solutions, if we know the reactions, then they will be very useful for finding the concentrations. Whenever acids and bases they react, the reaction is called as neutralization. These are some examples of neutralization reactions. HCl plus NaOH giving NaCl plus H2O. Both of them, they are strong acid and base. If we consider second reaction, nitric acid is strong acid, while K2CO3 is weak base. In the third reaction of sulfuric acid and ammonia, sulfuric acid is strong acid, while ammonia, that is weak base. And fourth reaction, acetic acid plus KOH, where acetic acid is weak acid, while potassium hydroxide is strong base. We have seen such reactions where the molecules, they combine in definite proportions, so the molar quantities are expressed in proper ratios, so that is called as stoichiometry. All the neutralization reactions are stoichiometric reactions, and based on such reactions, titration is the technique which is useful for finding concentration of the solutions. This method is called as titrimetry. Generally, whenever we are considering such reactions, in day-to-day life also, you may have seen such reactions. उदाहरणार्थ, काही वेळेला आपल्याला ऍसिडिटीचा त्रास होतो, so we generally take antacids. So, in our stomach, there is gastric acid, the quantity of which is increasing, and we become uneasy. In that case, we use the antacid, which is some weak base there which neutralizes that acid, and we get the relief. Or there is one more example. If there is an ant bite, there is some weak acid there which is introduced in the body. So in that case, we just apply some dilute solution of sodium bicarbonate, which is called as बेकिंग सोडा. खायचा सोडा आपण पाण्यामध्ये त्याचं द्रावण करून जर कीटक चावलेल्या जागी लावलं तर आपल्याला ताबडतोब रिलीफ मिळतो. These are some common examples of neutralization reactions in day-to-day life. Let us know about the exact finding out the exact concentrations, the technique used, that is titrimetry. Whenever we are using this technique, there are some important concepts which are summarized here. Analyte, that is the species in the sample about which analytical information is sought or the concentration of which is to be found. So, in any sample, some particular analyte that can be estimated. In titrimetry, the solution containing analyte is called generally as titrate or titer. For finding the concentration, we are using the titrant, that is the reagent of known concentration. It may be some standard solution. So here is one more concept, that is standard solution. That is the solution in which the concentration of a solute is known with high reliability. Using these things, we can use the technique titrimetry, that is the process of systematically introducing an amount of or volume of titrant which is chemically equivalent to the quantity of analyte in the sample. So, stoichiometric reaction that is followed, which is called as titration. As we are talking about acids and bases, so the technique is having some different name, acidimetry or alkalimetry. If we are carrying the volumetric acid using standard solution of acid to find the strength of base, it is called acidimetry. And if we are carrying volumetric analysis using standard solution of base to find the strength of acid, it is called as alkalimetry. Whenever we are using the solutions of known concentration, which are known as standards, There are some types. Primary standard, that is one important concept, that is a highly pure chemical compound which is used to prepare or determine the concentration of standard solutions for titrimetry. Using such solution, we can find the concentration. The process is known as standardization. So standardization is the determination of the concentration of solution by calibration or by titration, directly or indirectly using a primary standard solution, and this all process is standardization. There are also other type of substances which are called as secondary standards. A substance whose purity has been established and verified by chemical analysis is secondary standard, but there is possibility that the concentration of that may change as time proceeds. If we keep that solution for some time, there is possibility that atmosphere or atmospheric moisture may react with that and the concentration may change. For example, for sodium hydroxide, there is possibility that it may react with atmospheric moisture or the gas like carbon dioxide and the concentration of that changes. So sodium hydroxide is not considered as primary standard. Let us see some commonly used primary standards in acid-base titrations. For alkalis, potassium hydrogen phthalate, which is having the short form KHP, is well-known standard. Some other standards are succinic acid or ascorbic acid. You may be knowing ascorbic acid, that is vitamin C. For standardization of acids, we use the reagents THAM, that is tris hydroxymethyl aminomethane, which is one popular primary standard. Commonly available other primary standards are KHCO3, that is potassium hydrogen carbonate or potassium bicarbonate, and another one that is Na2CO3, that is sodium carbonate, which is known as washing soda. Whenever we are carrying this neutralization reaction by experiment, which is known as titration, we should get the end point when that reaction is complete, that is indicated by the end point. So the definition of end point is an observable change during titration that signals that the amount of titrant added is chemically equivalent to the amount of analyte present in the sample. So as that equivalence point reaches, you get some change, maybe some change in color or increase in temperature or some such type of detectable change. When we are getting such change, when both the quantities become equivalent. So equivalence point, that is another concept. This is the point in titration at which the amount of standard titrant added is chemically equivalent to the amount of analyte in the sample. So this is equivalence point, and generally the end point should come closer to the equivalence point. If this condition is fulfilled, then we can get the exact concentration by titration experiment. In laboratory, the colored compound, which is known as indicator. General definition of indicator is given here. Indicators are often added to the analyte solution to produce an observable physical change, that is the end point, at the equivalence point or near the equivalence point. Large changes in the relative concentration of analyte or titrant occur near the equivalence point region. These concentration changes cause the indicator added to change its appearance. For typical acid-base indicators, these changes include appearance or disappearance of a color. For example, for phenolphthalein added to the acid, if we go on adding base, it will become from colorless to pink. Or there may be change in color. For example, if we are using acetic acid to which if we are adding ammonia, or if we are taking HCl to which if we are adding ammonia, and if we use methyl orange, the color change will be from yellow to red. The indicator that changes color at or near the pH value at the equivalence point is best suited indicator for that titration. Now, what is this pH concept? That is one more concept to express the concentration. We are knowing that for acids, hydrogen ion concentration, that is rather important thing. If it goes on decreasing, the acidity will go on decreasing. For the solutions which are basic, hydrogen ion concentration decreases much. So the hydrogen ion concentration is expressed using the concept pH, and pH is equal to minus log of hydrogen ion concentration. We can get different colors using indicator for the solutions of different pH. Generally for acids we have the pH 0 to 7, while for alkalis the pH is 7 to 14. Here are some such color changes. At pH 0 or 1 we are having highly acidic or strong acidic solutions, while for pH 13 to 14 we are having strongly basic solutions. Here are shown the color changes as we go on changing the pH. And on the right hand side here, you can get here different commonly observed chemicals and their proper pH regions are indicated in this particular diagram. For example, battery acid, that is sulfuric acid, for which we are having the pH 1. Or for the baking soda, that is NaHCO3, we are having pH near about 8. Or for alkali solution, we are having the pH near about 13. So we use proper indicator for proper pH change near the equivalence point. We are considering here one simple reaction of HCl with NaOH, where phenolphthalein is used as indicator because for this reaction the pH for change is near about 7. For phenolphthalein, the color change is observed at the range 8.3 to 10. This is acidic type of indicator which generally is having tendency to react with water and give the proton, and after giving the proton it becomes pink in color. Let us consider another example. HCl is reacting now with weak base ammonia. Now the pH at which the equivalence point is attained is about 4, or at this pH we will get the end point. So the indicator selected is methyl orange, which is showing the color change in the range 3.1 to 4.4, and the color changes from red to orange to yellow. This indicator is basic type of indicator, that is, it accepts the proton and shows the color change. To remember the use of methyl orange, we can remember the word SWAM. That is, when we are carrying the titration of strong acid with weak base, methyl orange is used as indicator. इथे आपण बघतो की स्ट्रॉंग ऍसिड HCl आहे, वीक बेस हा अमोनिया आहे, त्यामुळे स्ट्रॉंग ऍसिड साठी कॅपिटल S हे अक्षर घेतले, वीक बेस साठी या अमोनियासाठी W अक्षर घेतलेलं आहे, ऍसिड बेस टायट्रेशन साठी A अक्षर आहे आणि मिथाइल ऑरेंज साठी M हा अक्षर वापरलेला आहे. Instead of indicators, we can use instruments also to get exact endpoints. These instruments respond to properties as color change, change in turbidity, म्हणजे सोल्युशन धुरकट होतं किंवा त्याचा क्लॅरिटी कमी होते. You may get the change in temperature or change in electrical properties such as change in current. So the solution shows such characteristic changes during the titration process. Let us know something about the apparatus used for titration. Whenever we are preparing the solutions, dilute solutions, we are using for preparing the solutions volumetric flask. This is a typical volumetric flask having a particular shape and its stopper, that is either ground joint stopper or plastic stopper, which avoids the losses due to evaporation. We can get volumetric flasks of different capacities starting from 5 ml and going up to 2 liter. So any solution that is first diluted, then let that solution attain room temperature, and then only it is diluted to the mark which is seen in this neck of the flask. Then from this solution we may take small known amount which is called as aliquot of the solution, and for that pipette is used. Here is the picture of the photograph of the pipette. It is the device to permit the transfer of known volume of solution from one container to another, that is from the volumetric flask to a small beaker or to conical flask. Whenever we are using the pipette, you should not pipette out the solution by mouth, but you should always use some rubber bulb for transferring this solution. So in this photograph, that rubber bulb is shown, and also the beaker in which the solution is to be transferred, that is also kept side by side. The pipettes are of two types. One type, that is volumetric or transfer pipette. It is the device which delivers a precise volume. So you may get the pipettes of capacity 10 ml or 25 ml. There is another category which are called as graduated pipettes or measuring pipettes. Using such pipette, you can deliver any volume of the solution. So that pipette, if it is of 10 ml, using that you may take from 1 ml to 10 ml, any volume can be taken, because on that pipette there is that graduation scale there. So you may take any volume using such measuring pipette or graduated pipette. These pipettes are used in various laboratories, and so they may be of different types. For example, in clinical laboratories, whatever the pipettes used, they are called as clinical or serological pipettes. Always keep in mind, no solution should be pipetted out by mouth. So pipettes are always filled by suction, that is by creating vacuum, which is created using either rubber pipette bulb or a pipette pump, which is called as vacuipette, or other such pipetting device. For taking another solution, you can use the burette, which is a long graduated tube having stopcock at the bottom. So it is graduated tube which is accurate, which can take accurate volumes in the flask. It has the glass stopcock or Teflon stopcock to control the volume which is dispensed. So whatever the solutions which we are taking, we can take them using proper control of the stopcock there. Here is that shown the scale which is seen in that burette. Generally here, whatever the level of the liquid, there is, you can see the meniscus, that is some curved part that is there. The basic lower part of that curve, that is considered there for taking the volume of the solution. For example, for this solution, the volume indicated, that is 35 ml exactly. About this apparatus and about this technique, in brief, some history can be given. Actually, this technique was developed in 18th century to find out the titer value, that is how much concentrated the solution is or how much good that solution is. In textile industry, there was the use of KOH or some acids like nitric acid, for which the concentration was to be found, and for that the technique was initially developed. They were using at that time tablespoons for taking the solutions, but later there was developed some apparatus for that. For the neutralization reactions, initially there was no proper indicator, but the effervescence, that is evolution of CO2, that was the indication there, but you cannot get the end point exactly there in that acid-base reaction. And William Lewis was the first one to use litmus paper to indicate such change, where we have seen such color change in acids and bases in our earlier discussion. Francis Descroziers was the first one to use some lab glassware for titrimetry, while Gay Lussac, the famous scientist who worked related to gas laws, was the first person to give the names for these different apparatus as well as for the solutions. André Urey introduced the equivalent weight concept, while Frederick Moore was the person to use the normality concept. He was the person to summarize all the analytical procedures in his book, and this book was very popular because there were several editions of that book related to titrimetry. Now let us know something about titration procedure, some do's and don'ts while doing that titration experiment. Always, whatever that apparatus which we are using for titration, it should be clean and dry. So always take care before the experiment that whatever the apparatus should be cleaned thoroughly and dried. About the burette, make sure that stopcock of it is secured tightly enough to prevent leakage, but it should not be so tight as to make the rotation hard. So you have to check that stopcock before filling that burette. Before using these, if you want to use the burette for the alkali, rinse that burette with alkali solution to be used. If you want to use the pipette for acid, it should be rinsed with that acid prior to taking the exact volumes. For these, whenever we are taking the exact volumes from volumetric flask, take care that no air bubble should remain in the burette, in the barrel of the burette or in its stopcock, or no air bubble should remain at the tip of the pipette. You can take the definite volume of that solution in the using pipette in the conical flask and then can start the titration. Before starting titration, select suitable indicator and add a proper amount of that indicator in that flask. Generally, try to utilize minimum amount of indicator, otherwise it will consume some of the reagent which is to be, the concentration of which is to be determined. The titration is generally performed in a conical flask which is also known as Erlenmeyer flask. This flask is generally placed on a white background and the tip of the burette is positioned within the neck of the flask. For getting white background, generally we are using white porcelain tile on which this flask is kept. Generally we are using titration stand to which the burette is secured vertically, and below the burette is kept that conical flask on that porcelain tile. And then when we are adding the solution from the burette, the flask is swirled with right hand while stopcock is manipulated, that is put on and off periodically using left hand. Whatever the procedure comfortable can be followed here while adding the solution from the burette. always one has to take care that you should add the solution in portions, maybe in drops, and you should go on swirling the flask. म्हणजेच आपल्याला मराठीत म्हणता येईल की ब्युरेट मधनं आपण ज्या वेळेला सोल्युशन कोनिकल फ्लास्क मध्ये घालत असतो त्यावेळेला फ्लास्क सतत हलवत ठेवावा. हलवताना काळजी घ्यावी की त्या फ्लास्क मधलं सोल्युशन बाहेर येतं उपयोगाचं नाही, पण हे सोल्युशन व्यवस्थित मिक्स झालं पाहिजे. Whenever we are adding that solution, we are always trying to find the volume, whatever is added from the burette. Always see that there should be no parallax error. That is, you have to see the level by keeping your eye in the level of the solution. So there should be alignment of the observer's eye, the meniscus of the liquid, as well as of the scale. As the titration proceeds, the indicator shows the change in color. When the equivalence point reaches, you will get the clear end point. The color changes quickly. There should be sudden and permanent change in color, and that change color should remain for about 30 seconds. If that color is still vanishing, then you will have to add some more amount of the solution from the burette. Many times, instead of adding drop as such, you can add the fraction of drop also. In that case, you have to just put the stopcock off and take whatever the fraction of drop coming out by putting the side of the flask near the burette, and then using wash bottle you can transfer that drop to the conical flask. In this way, you can take exact end point of the titration, and which will be indicated by the change in color of that of the indicator. After the titration is complete, unused titrant should never be transferred to the original bottle. So this precaution should always be taken. After performing first titration, which is called as pilot titration, we can calculate the approximate volumes for the next coming titrations. So later coming titrations you can do more carefully. That will save time also. Many times, rather than diluting the solution and taking the aliquots using pipette, you can take the solid small amount of weighed amount of solid in the flask itself, add to that some water, and allow it to dissolve completely, and do the titration by adding the volume from the burette itself. This will minimize the errors in weighing as well as in the transfer of the solution. We have talked about the litmus paper. So what is litmus? Let us know. It is actually a natural pigment obtained from archil, that is dyer's moss. This is one type of moss. From this, after adding ammonia solution, that colored pigment that is extracted in that ammonia, this ammoniacal solution becomes colored, from which the dye can be extracted, and it can be used for preparing litmus papers. Litmus paper generally turns red in acid, and in base it becomes blue. So that is a very typical indicator used in acid-base titrations. The pH range is indicated, that is 4.5 to 8.3. You yourself can prepare some colored indicators from naturally occurring materials. Some examples are given here. You can prepare indicator from the flowers of bougainvillea. मराठीत आपण त्याला बोगनवेल म्हणतो, किंवा रंगीत फुलेही चालू शकतात. उदाहरणार्थ जास्वंदीचं फुल आहे, त्यापासून आपल्याला इंडिकेटर मिळवता येतो. और वी कॅन यूज द लीव्स ऑफ रेड कॅबेज, लाल कोबी वापरून आपल्याला इंडिकेटर मिळवता येतो. और रूट ऑफ बीट, बीटचं मूळ लाल असतं, त्यातनं आपल्याला इंडिकेटर मिळवता येतो. और फ्रॉम द फ्रुट्स ऑफ जामुन, जांभळापासून आपल्याला उत्तम इंडिकेटर मिळवता येतो. How to prepare this indicator? You can take the colored material, convert it into small pieces, add to that small amount of alcohol, which is generally called as spirit, mix it thoroughly well. You can use mortar and pestle for mixing that. then filter that colored solution to remove whatever the insoluble matter, and then that colored solution will be useful as indicator. You can test the color changes by using different types of acids and bases for such indicators. So this is some interesting part related to preparation of indicators. Let us have one problem related to titrimetry, which can give you the exact concentration by calculations. In this titrimetric estimation of the ion carbonate, it is CO3 - from some water soluble sample of medicine. For example, we can use some antacid there, from which you can determine carbonate. Now the problem is given. 1 gram of carbonate was analyzed by titration using 0.202 molar HCl, that is hydrochloric acid. So the titration is carried out. You have to calculate the actual amount of carbonate. The titration reading given here, that is 24.2 ml. Now for calculation of carbonate concentration, we may require the molecular weight of that, for which atomic weights are also given. Now let us solve this problem. The actual reaction taking place here, that is carbonate reacting with HCl. 1 mole of carbonate ion reacts with 2 moles of HCl to give CO2, water and chloride ions. Using this reaction, which is used for titration, let us do the calculations. We have calculated the molar mass of carbonate, that is the sum of atomic weights. So atomic mass of carbon plus 3 into atomic mass of oxygen, the total is 60. Now 1 gram mole of carbonate will require 2 gram moles of HCl, as we have seen by the earlier reaction here. In other words, we can say that 2 gram moles of HCl neutralize 1 gram mole of carbonate, that is 1000 ml of 2 molar HCl will be required for titration of 60 grams of carbonate ion. Now actually, for the titration, we are required 24.2 ml of 0.202 normal HCl. So using that, we can calculate the exact amount. So all the calculations are shown here. So that amount is 0.2933 grams of carbonate. Now actually our sample was 1 gram sample, which is containing 0.2933 grams of carbonate. So 100 gram sample will contain 29.33 grams of carbonate, or the percentage of carbonate in our antacid we can express as 29.33%. So this is something actual application of titration for finding out the concentration of an antacid. So let us summarize whatever we have studied in this topic, acids and bases. We have talked something about the strength of the reagent, whether the reagent dissociates completely or partly, that is indicated by strong and weak concepts. To express the actual amount of that solute added in the solution, the concentration concept is there. If the solution is having much higher concentration, it is called as concentrated. If it is if water is mixed to that, we get the diluted solutions. So concentrated and dilute are the terms to express the concentration. We can use here the concepts as gram mole or gram equivalent to express these concentrations. For moles, we are using the concept molarity, while for equivalent weight, we are using the concept normality. Then when we are making the acids and base react together, that is the stoichiometric reaction, which is used for finding out the concentrations using the technique titration. So we have talked something about different apparatus used for titration as well as the process of titration there, actually how to do that titration. Before that, we have also seen the history of titration, titrimetry also. Then we have talked something about the do's and don'ts of that particular titration procedure, which things are to be followed and which things are to be avoided. So this is something about the actual titration experiment which we generally carry in laboratory to find the concentrations. And at the end, we have seen the actual application of this titration for finding the concentration of an antacid. So in this way, we have talked something about the acids and bases with reference to the concepts as the strength of the solution, the concentration of the solution, the neutralization concept and its application to the actual work there related to analysis, that is titrimetry. These are some references which are used for this particular talk there. The books for standard 9th and 10th, as well as there are some books related to analytical chemistry, book by Skoog and West or book by Christian, they have been used here. And for finding the history of analytical science, the Encyclopedia of Analytical Science that has been used. These are the websites where you can get some other useful information. For example, in the first website, you can get some useful information related to the titration part there, how to carry that titration using computer program. While in the second website, you can get some information with the help of photographs, how to do this titration procedure effectively. If you are having any queries or any problems, please feel free to contact us. I am Dr. V.D. Kelkar, so my email address that has been given, मी Dr. Vikram Kelkar, माझा email ID दिलेला आहे vdkel@kem.unipune.earnet.in, and there is one more email ID that is of Professor Kale, Yashodan Kale, that is ygkale@mkcl.org. Thank you very much.